So today's topic is, let's see, that's the digital sensor interfaces laboratory, and there's the laboratory exercise like that, where we actually have the PSOC circuit and then three different kind of digital sensor interfaces for the sensors. So there's a SPI, and then the second one is the one-wire sensor, and third one is I2C sensor. So those are the most commonly used serial interfaces to any digital sensors. And then, okay, there'll be even more serial communication, since there's also the USB to serial a bridge that you'll be using, and we would use this kind of device, which is a that's the PSOC 5 kind of rapid development board, but it also has this bridge already there. We don't need to invent that one over again. Easy to use. You just plug it in, and then you can actually, it shows up as a virtual serial port on computer, where you can then set the parameters for data transmission, and then basically there are a couple of pins, the receive data and transmit data pins here, that you can plug the other PSOC board by wires. Okay. So there are basically four different the serial lines on this exercise. In addition, of course, we will have their LCD just for, you know, the debugging and to show that there is some data. But anyways, those three sensors, I actually also recommend you adding those sensors in this order, since they are basically the easiest one is at the top and the hardest one is at the bottom. Okay. So first of all, let's see, one wire sensor. This is a typical one wire temperature sensor. That's probably the most used sensor in the world. Actually, the model 22 plus would be. This is the old-fashioned model 20, but they are basically, I think they are compatible, code compatible sensors. Maybe we should actually use the correct temperature sensor. Yeah, we probably should use the DS1822 plus datasheet. There's a wrong link. But they are code compatible. Anyways, but there's a couple of tricks on this sensor. So first trick is this can use the parasitic voltage to power it up from the data line. And basically the common connection would be, oops, all right, just like that. So there is the power supply, a resistor pull down or pull up resistor to the data line, one wire data line, and then ground connection. And the VDD actually can be left unconnected. Okay. And the sensor itself has a lot of stuff there, especially it has a lot of registers. And you actually need to read the manual quite, the datasheet quite throughoutly to find what kind of protocol it actually uses. What to write there, what kind of response you would expect to have back. Okay. I saw this same sensor used in one of chaos courses. Have you used that one?
I don't remember if it was in chaos course.
Yeah. Okay. Okay. So yeah. So but anyways, so it's one wire. It has its own protocol, and then basically you just need to read the datasheet. Although probably you would like to read the datasheet, the correct one. So it will be 22. And let's see. Yep. Or actually, yes. That's the DS1822. Does it give actually the plus there? All right, 1822 plus. Yeah. All right, now it's updated. I just love the Google Docs immediately when you have done the changes. They are there. Okay, no emailing of them. Okay, so basically that's the data sheet, which also shows you the what kind of register this device have. Okay, temperature register format is there, and I think there is also an example code. Okay, this is very important picture down there. It shows the memory map. When you are reading stuff from the this device, you actually are reading different values, all kind of stuff there from the device, not just the temperature itself. Okay, configuration register CRCs checks hardware and then let's see. Okay, there's DS1822 operation example 1. That's also gives you excellent startup point to write your own code. So what you need to do is to on PSOC you initialize a one wire device. There are instructions how to do it, and then basically you need to do these the one wire commands there on different modes. Okay, let's see, master sends. So master is your PSOC, and basically okay on the reset. So everything starts from the one wire bus reset. Then basically that if there's any devices, they would respond to that one. If there's only one device, that's actually quite fortunate, since basically if there are more than one device, then you should do the protocol 2, finding which devices are there first and then continue. But now we have only one. We can use so-called addressless mode of operation. Okay. So, but anyways, you can find everything basically. Okay, you can find everything from the datasheet. It requires some reading of the datasheet, but anyways, that's what you signed for. Haha. Okay, and then how to use the PSOC, these the one wire module. That's basically quite straightforward when you follow the instructions. First of all, the digital communication blocks are all here, including the one wire module. Okay, there you go. And you just need to set up the clock according to the specifications. So there you need to basically compare the datasheet of this PSOC one wire module with your device. I think there are pretty good examples of how to use that one. Okay. And just configure and then find a way, which is also on the application notes, how to use the same pin for input and output. All right, so basically you need to also check the application note from Cypress. That actually helps you to start with this one way of interfacing with the sensors. And by the way, there is a example on that 18S20 type of temperature sensor, so I would guess there might be actually even some examples. Might be. If you find it from the internet, it's free, right? All right, so yeah, so that's the first part. And when you get this one running, basically first check it with the LCD. That basically gives temperatures that make sense. Same way as for the LM35, we have about 23 degrees Celsius here, so that's what you should be expecting from the sensor reading. And then of course when you heat it by your hands or by just blowing some air in it, it should actually rise a little bit. On this exercise we are not interested about the exact values, but how to get the data flowing. Okay, and then when you have that value on LCD, would be a good point. You already have one, right? How about you? That would be a good point to try to send the data to computer. So how to transfer data to computer? We will be using, let's see, just for fun, using this device. Oops. With this PSOC 5 stick board and with the USB connector on the one end, and then on the other end there's the this is the connection for your the other PSOC board. This one plugs to the computer, and that would be your wiring would from your device would come to here, and the pin out is actually on the bottom. All right, it doesn't focus well, but anyways, there's a pin out on the bottom. So UART RX is 12 point, is it 8 or 6? 6, okay. And transmit is 12.7 pin on the corner pin. And by the way, it doesn't work without a common ground. So you also need to actually have a wire from common ground, which should be on the other corner here. Please observe that there's also one pin actually open right there. Oops, where? There, it's intentionally left open. That would be the power pin. Okay, so if you do this kind of boards yourself, you might actually consider leaving that kind of power pin also unattached. Otherwise, you'll be shorting ground with power. Not a good idea. Okay, so I'll show you what happens when you plug this device in, the PSOC 5 board. Okay, and what I should take here is the let's see, control panel and the device manager. With the device manager. Device manager. Ah! Don't say that I cannot use the device manager here. Okay, view. Okay. That's fine. So device manager is running, and currently we are looking at empty COM ports. When I plug this one on the in here, all right, your device is ready. Ha! There you go. Now I have USB UART on COM9 port, and on from here you can actually see the current settings. So this device works as just like any other COM port with the 9600 bits per second, 8 data bits, no parity, 1 stop bit. Excellent. And no flow control, meaning that you need to be a little bit careful from when you are sending data. Receiving, no problem. It has a very deep buffer, and computers are rather fast nowadays. So everything is better nowadays, or at least faster. Okay, so yeah, make note of that port. And by the way, if you unplug that one from one USB port and then put it on another, it might actually change the COM port. All right, and if you have similar ones, they basically go into different places, so every time you need to check that which COM port it is. Okay, and COM port, how to then basically see what happens on the COM port. Easiest program would be putty. Excellent. And there, just serial port COM9 open. Okay, now this is connected directly to that device, and it shows here whatever data is transmitted through this bridge. Okay, so that's the easiest way of testing your data transmission. How to then save that data, well, that's another course. If you are familiar with the lab view, that will be probably the easiest way of doing a data logging. Yeah, data logging using LabVIEW, or well, MATLAB works too, and you can even make macros on Excel to do that, and or write your own code. You should be able to do it. I think it's something like 5 lines of Java code if you want to do it yourself. You know, some sort of simple terminal. Okay, so back to the business. So we are actually, let me check that I have the correct view. So now we have that PSOC 5 board there just to bridge the data, but we are actually working on these PSOC 1 boards. So this design is for PSOC 1. The PSOC 5, the development board, uses totally different tool chain. So it's only the programmer part is a common, but otherwise it uses the PSOC creator software for the development. This uses this PSOC developer. Okay, anyways, for that data transmission, for this exercise you would need only TX8 module, so one directional, you're just sending. But if you want to, you can actually add there even this UART device. I don't care how you make it, but anyways, the minimum requirement for this exercise would be to have the transmit data TX8 kind of module there, and configure it so that it has the same parameters as the this bridge board. And then hint about the wiring. So PSOC 1, and that's the PSOC 5 board. There you have the TX, RX, and ground. Same thing there, you have the ground, RX and TX. So remember to hook up the ground wire, so that's the reference for the signal, and then this one transmits and this bridge actually receives. So this is configured as a similar DTE device as any other. So common mistake is actually to have the straight lines there, which would be kind of how bridge should operate. So bridge is a modem kind of device. And if it doesn't start working like that, then try the other way around. Okay, all right. But anyways, the wiring, basically without this ground wire, absolutely no guarantees that it would work, because they basically need to be connected on the same ground at some point. Okay, this one basically connects to the PC, the USB port. So that's the USB. And so basically does the other one too. So basic, there's the mini prog. And that also goes to a USB port of the of the computer. There's no guarantee, especially on the laptops, that these would be connected at all. Absolutely no guarantee. They can be totally separate. Can be. Most of the time they are not, but anyways, they are still kind of long cable here and some open wires here, so if you leave that one out, you'll get actually a common mode noise in between, and that'll do your data transmission. Okay. So yeah. So the one wire, then this what kind of connection or transmit data connection. I should actually move the LCDs and that kind of thing up there. But anyways, well, if you followed, you got my point here. The point is not to put everything there and start wondering why nothing works, and then find out that okay, LCD module actually requires lower than 12 megahertz CPU. I found it out yesterday. So if you are using LCD, use CPU speed sys clock divided by 2. It doesn't work at 24 megahertz CPU speed because the delay is done by knob operations on assembly code. It's a software kind of the module. All right, so one wire done and checked, and everything works just beautifully. The next point would be this MCP 3201. Okay, which is SPI A to D converter. It has 12 true bits. And that's also one excellent place to use successive approximation register kind of A to D converter, since the whole idea to have it on SPI bus kind of supports it. Remember this SAR type successive approximation type A to D converter. It gives you basically each bit one by one, starting from the most significant bit for every single the sampling clock or the data clock. So what we would be expecting to have here is basically 12 bits of data one by one, starting from the most significant bit. Excellent. The other stuff is they're also pretty cheap, so this is very cheap A to D converter for plenty of different purposes. Couple of notes which I have also kind of given you some hints how to connect this one. So reference. So VSS is ground connection. Then on the top corner there's a VDD, which is the power supply. In our case that goes to 5 volts. Okay, the input signal. Input minus signal is the local reference, and that this actually gives unipolar data, unipolar digitized data compared to this one. So basically this gives you the lower limit of the A to D range. Most of the time this should be also connected to VSS. Then this is your input signal, and since we have that LM35 analog sensor, that's just fine signal source. So then we have 10 millivolts per centigrade here. Okay, and then it also needs some power. So from +5, that's just fine. And again, remember to check a couple of times before connecting, not to destroy that LM35. Okay, reference. Now we're actually using a little bit better reference. Should I distribute these now? We are using 4.096 volt reference with this 2 to the power of 12 millivolts. So that's the reference. Save them so that you can actually find them again, since they have the same yeah. Oh, you have all. Okay, yeah, I'll leave it here. Unless you can read that fine printing, so you can separate from the LM35. It's the same package, similar package, so easy to mix. Then the A to D converters. Do you have a knife? Anyone? Knife? You have a knife, yes. Thank you. That's the A to D converter. Here. Here you go. And by the way, it's a good idea to stuff them on that this conductive styrofoam on this the evaluation kit. These are electrostatic sensitive devices, but well, I haven't destroyed any of these for 25 years or so. So basically, when you are handling this kind of electrostatic devices, you should handle them not too carefully. When you are too careful, you can zap the pins, but if you are just taking them from the several pins, there's usually if there's any charge, it goes like this, not like okay. Yeah, and then there are these SPI signals. Chip select, digital out signal, which is actually master in slave out, and that's the serial clock. I think it's the on SPI it was SCK. Okay, so those are the connections. Then you need to check out how fast this can go. This is pretty fast, actually. You can run it. I think that was was it up to 8 megabits per second transmission. And the protocol. Protocol is most significant bit first. Okay. But, all right, let's take a look at this. So this is how the data is read. When you set the chip select signal down, then you start transmission. So first 2 bits on what you receive on MISO line are actually the high Z signals, so they can be anything. So scrap those. The following signal, the bit is actually the null bit. Let's draw it a little bit so we have the so on, tick tick tick. So doesn't there so this is basically 1, 2, third bit, which is the third from the high end, most significant bit first. Okay, so that's null, and then basically you have 12 bits of data. So that is the most significant bit, and so on. And here you have the 12 bits. Okay, but if we wasted 3 bits here, it means that the first byte what you get from the SPI transfer, first byte actually is such that you have only, well, that's something, this should be 0, and this is the 5 highest bits of the data payload. And then you have the byte, the second byte what you read, you have the rest, 7 bits. And the last bit on this one would be whatever. Now the question is how to make this one to make any sense on your data voice. Basically, this is easy part. But this is the lower byte. This is the higher byte, or actually, well, so that will be the highest nibble here. So what you need to do here is some bit shifting and the bitwise operations with these variables. So basically, byte 1 should be shifted 1 bit right. Okay, how to do it? What is the operator? Right? That's the easy part. Then basically how to shift that one accordingly and take care of that if there's some, you know, extra high bits here, how to scrap those. So basically what you need to do is first do some bit mapping, bit masking. So mask those bits out, and then basically have just those 5 bits and make an unsigned integer. So that you have those 7 lowest bits here, and then 5 other bits here. It's a good exercise to figure out how to do that. It's doable. And yes, you can use also multiply operations and that kind of things on the on your calculations. Mask this one, multiply it so that this bit actually hits exactly that one. That's one way. All right, and then you might actually also use some data casting, not to overflow your intermediate results and such kind of thing. But well, that's the basic principle how to get the data out. So first you need to have the correct connections, of course. There you have the this plus 4.096 volt reference from the chip I gave you with the okay data sheet. Yes, data sheet like that. Then you need to add on your design, you need to have the SPI master module, configure it, and make sure you got the right pins on the these lines, and that's it. Then some software, then you're done. Okay. Historically, this has been the trickiest part, how to shift the bits on the right place. Okay. Then the next bus would be I2C. Did I give you those 1822s? No, not yet. I'll also distribute these at the same time. So we have a I2C temperature sensor. Oh yeah, and I saw that one already used with the LPC stick. Just was it on Monday classes. This might be familiar. Okay. And again, so the SPI bus itself, it's simple. It's simple since it's very simple protocol to follow because there's no addressing as such kind of thing. You read and write directly to a device. You know you are reading and writing because there's a chip select, separate chip select signal. Okay, on this I2C bus, again, just like one wire, I2C bus also has the addresses. And here, these devices are always addressed. The one-wire devices usually have the addressless mode, so you can use, if you have only one on this one wire, one sensor on one wire bus, you might actually be able to just use it without any addressing, because the address recovery, it's not that straightforward anymore. On the other hand, there are plenty of rewritten code already available. I2C bus is you need to know the local address of the device. And let's take a quick look. So actually this device, well, it maybe tells the address. Hopefully it is somewhere in here. Okay, but anyways, yeah, there it is. So this device has a I2C slave address of 1001.101 binary. Okay, so that's the address. That's nice. Then we have this on what else you need there is the pull-up resistors on SDA and SCL bus. Okay, so on PSOC, let's get the I2C master. Oh, that's nice. This I2C master is actually software I2C. You can actually use even the software I2C bus master. Or there's also the hardware version, I think. Single master. No, this is also okay. Sorry. I2C actually is its own device inside of. It has its own engine inside of this PSOC. That's the native data transmission type for the PSOC. Okay. So, anyways, any one of those I2C master kind of things. This easy I2C is basically how to make the PSOC circuit as a I2C slave device easily. So you can then set the address of this device and then access with from another device. Okay, that's a quite nice actually. As I mentioned earlier, that for example the Raspberry doesn't have any A to D converters. Okay, today's exercise have the this MCP 3201. So connect MCP 3201 A to D converter to your PSOC circuit, make the connections, couple of external components, and make it a I2C slave. Then you have basically easily accessible the digital analog to digital converter for Raspberry. Okay. So a couple of comments here. Again, you need to basically go through of the how to access the data. So for example, there are 3 different ways you basically access the data or access this device. You can write bytes or byte. Can you see any mentioning that this device can take several bytes on one transmission? No. So every single byte what you get from this temperature sensor must be read separately with different transactions. For example, the okay. Register, read temperature. I think the temperature register okay, register summary, configuration register. Does it have any? Is this a 1 byte interface or several bytes? Oh, okay. So basically, it's a kind of linear Okay, 1 byte gives you the temperature. Okay, that's nice. That's really nice of them. It's on 1 byte only, but you need to just find the correct register. Yeah. Okay, but anyways, again, read that darn data sheet. Yeah, so that was the big one is the I2C temperature sensor. Then, yeah, that 1-wire temperature sensor. Sorry, I forgot. That's the DS1822 plus. Okay, there you go, DS1822 plus. That was the 1-wire. So, at the end of this exercise, again, as you can see, this is fairly straightforward exercise, but there's a lot of things to do, a lot of things to read, data sheets. Why I'm asking you to do it? Because it's called engineering. So, in real life, you may be lucky and you get into a situation that you need to interface a sensor with some system. And now you basically get the fundamentals of the 3 most common, or well, 4 most common serial interfaces in the world, which are the I2C, SPI, 1-wire, and then this normal UART. If you want more information about how about the USB, we don't have that course anymore. To go through all the USB stuff would be a 5 credits course. So it doesn't quite fit into this 5 credits course. Okay. But it's the piece of work also have the probably easiest devices available on the USB world too. So easiest the development tools. Maybe not. At least the best connectivity to anything else. All right, so let's wrap up. So, yeah, the 1-wire temperature sensor connected to PSOC, then this LM35, which is connected to SPI A to D converter. Then I2C temperature sensor connected to PSOC. All of those data should be shown in LCD and also sent as ASCII coded decimal numbers to the serial bus, and of course shown on a PuTTY or other terminal. Okay. The how to use that serial to USB adapter, basically, I have a small document there too. But I showed it already, so we are using this one. Yeah. So that is the tutorial for the lab today. Good luck. But it's, as I said, this is not hard. It's just hard work. Well, it doesn't really matter as long as you take one sensor and make sure you can actually show the result on LCD, and then also check that you can send the same data to this comport, or the serial, the virtual comport, then you are in a very safe grounds when you have the first sensor reading there. Okay, so I think that's more or less like 60% of the stuff is done already there. Then these other two sensors, it's just again, it's just you have to do some studying there compared to the PSOC or the nodes and the application nodes and the device nodes. Try to make everything click. I'll be here until 2:30 today. Any other questions? Okay, good. Start working.